Welcome to the Manufacturing Lithium-Ion Batteries, a practical introduction course. This lecture focuses on Chapter 1, Introduction to Batteries. Learning objectives. In this session, we'll build a clear foundation for understanding how batteries work, their structure, types, and key performance concepts. We'll also look at where lithium-ion batteries are used today, from portable devices to EVs and large-scale energy storage. This overview will prepare us for the more advanced manufacturing topics coming next. Terminology. Let me quickly walk you through a few key terms. A battery cell is the basic building block, the part that actually stores and releases energy. Cells come in different shapes, such as cylindrical, prismatic, or pouch-shaped. When we group several of these cells together, we get a battery module, which adds structure, cooling, and some monitoring. And when multiple modules are combined with protection hardware, cooling systems, and the BMS, the result is a battery pack, the complete unit used in EVs and ESS. The Battery Management System, or BMS, is basically the brain of the pack. It monitors voltage, temperature, and state of charge to make sure everything stays safe. The images here show how each cell type becomes a module and, eventually, a full pack, so you can visualize the entire structure. Let me read the brief definition of intercalation. Intercalation is the insertion of molecules into a host structure. In lithium-ion batteries, lithium ions are intercalated within the structures of the anode and cathode to facilitate battery operation. Now, what does that actually mean? In a lithium-ion battery, both the anode and the cathode have layered structures, almost like bookshelves. During discharging, lithium ions leave the anode and move through the electrolyte toward the cathode, sliding into those open spaces, while electrons travel through the external circuit to power the load. During charging, everything is reversed. An external power source pushes the lithium ions back to the anode and returns electrons through the circuit. The two diagrams on the slide show this process visually. The discharging image shows ions moving from the anode to the cathode, generating electrical power. The charging image shows the ions being pushed back to the anode by the charger. Intercalation is what allows lithium-ion batteries to work repeatedly and safely. It's the reversible movement of ions in and out of those host structures. Battery structure. On this slide, we're looking at the basic structure of a lithium-ion battery. Every cell is built around a few key components. We have the anode, the negative electrode, and the cathode, the positive electrode. These are the two materials that actually store and release lithium ions. Between them is the separator, a thin, porous film that keeps the electrodes from touching while still allowing ions to move through. The electrolyte, shown in the center, is the liquid that carries lithium ions during charging and discharging. And on the outside of each electrode, the current collectors, copper for the anode and aluminum for the cathode, move electrons to and from the external circuit. The diagram illustrates how these layers come together inside a real cell. It's a simple layout, but this structure is the foundation for everything a battery does. Fundamentals of energy storage. Let's quickly revisit what a battery actually does. A battery is simply a device that stores energy chemically and then releases it as electricity when we need it. During charging, we supply electrical energy to the cell, which is stored in the chemical bonds of the active materials. During discharge, those chemical reactions reverse, releasing the stored energy as electrical power to run a device. The diagram here visualizes this process. Ions move through the separator, electrons move through the external circuit, and the cell alternates between storing and delivering energy depending on whether it's charging or discharging. Energy storage characteristics. Lithium-ion batteries are widely used because they pack a lot of energy into a small, lightweight package. From the phone in your hand to an electric vehicle battery pack, the same core advantages apply. Here, we highlight three of the most important characteristics. Energy density tells us how much energy we can store for a given size or weight. Efficiency reflects how well the battery stores and releases that energy without major losses. And scalability means we can build these systems larger, like in EVs and grid storage, without sacrificing performance. You can see that contrast in the images, a slim phone battery versus a much larger EV module, both relying on the same lithium-ion principles. We'll look more closely at energy density in the next slide. Energy density tells us how much energy a battery can store for its size or weight, and it directly affects how long a device can operate before needing a recharge. We usually look at it in two ways: specific energy in Wh per kilogram, which matters when weight is critical, and volumetric energy in watt-hour, Wh, per liter, which matters when space is limited. The chart here compares several battery chemistries. You can see why lithium-ion dominates today. Its energy density is dramatically higher, typically around 150 to 250 Wh/kg. Lead acid and older chemistries like NiCd or NiMH fall much lower on both axes. But even with lower energy density, those older batteries still have their place, especially in stationary systems or applications where weight isn't the priority, or where cost, temperature tolerance, or specific electrical characteristics matter more than packing in the most energy. So overall, this slide highlights why Li-ion became the preferred choice for modern mobile and electric applications. Battery specifications. On this slide, we're looking at a comparison table outlining the key specifications of major battery chemistries, lead acid, NiCd, NiMH, and several types of lithium-ion. It's essentially a snapshot that helps us understand why different batteries are chosen for different applications. One item I'd like to highlight is cell voltage. Notice how traditional chemistries like lead acid or NiMH sit around 1 to 2 volts per cell, while lithium-ion chemistries deliver much higher nominal voltages, typically around 3.3 to 3.8 volts. This higher voltage contributes to better energy density and improved overall performance. And if you scan across categories, cycle life, charge time, maintenance needs, peak load current, you'll see why lithium-ion dominates today's markets. It delivers strong performance, low maintenance, fast charging, and long cycle life, especially compared to older systems. The table is dense, but the takeaway is simple: lithium-ion offers a superior balance of energy density, efficiency, and usability, which is why it has become the standard for EVs, portable electronics, and energy storage. Slide 1 of 4 for battery efficiency curve. On this slide, we're looking at the overall efficiency behavior of a battery as it charges and discharges. The curve helps us compare the energy we put into the battery with the energy we actually get back out. You'll notice the graph is tied to the state of charge. In the middle range, roughly 20% to 90% SOC, the battery operates most efficiently. But as we move toward either extreme, near 0% or 100%, the voltage becomes unstable. At low SOC, the cell experiences high discharge stress, and at high SOC, charging stress increases. Both ends lead to efficiency losses and long-term damage. The key takeaway is that batteries deliver the best performance and longest life when operated within their ideal SOC window. Slide 2 of 4 for battery efficiency curve. Here, we start looking at what affects battery efficiency. One major factor is internal resistance. When resistance is high, more energy is lost as heat, and the battery simply can't perform as well. Temperature also plays a big role. The graph shows how the same Li-ion battery behaves at different temperatures. At normal room temperature, around 20 degrees Celsius, the voltage stays stable longer. At higher temperatures, such as 55 degrees Celsius, the battery delivers even better performance and a longer discharge time. But at low temperatures, such as -20 degrees Celsius, efficiency drops sharply, and the voltage declines much earlier. Overall, this slide reminds us that both internal resistance and temperature can dramatically impact usable capacity and overall battery performance. Slide 3 of 4 for battery efficiency curve. Here, we're comparing different battery chemistries as they discharge, and the graph shows how cell voltage drops as the battery approaches empty. You can see that lithium-ion and zinc, manganese dioxide cells experience sharper voltage drops near the end of discharge. That means their usable energy declines more quickly as they approach 0% state of charge. On the other hand, lead-acid batteries maintain a flatter voltage curve and perform more consistently at low SOC. Therefore, in applications where preserving every bit of available energy is critical, like backup power or certain stationary systems, lead-acid may still be a better fit. The key takeaway is that the best battery depends on the application and how much low-voltage performance matters. Slide 4 of 4 for battery efficiency curve. Now, let's wrap up the efficiency discussion by looking at how battery health and efficiency change over time. The graph here shows how cycle life is strongly tied to temperature. Batteries last the longest in their ideal operating range, roughly room temperature up to around 40 degrees Celsius. Below about 10 degrees Celsius, we start to see losses due to lithium plating, and above 60 degrees Celsius, the chemistry breaks down quickly. We also evaluate battery health using 3 efficiency metrics. Coulombic efficiency tells us how much charge we get out compared to what we put in. Energy efficiency is measured as the watt-hours delivered divided by the watt-hours absorbed. And the voltaic efficiency compares discharge voltage to charge voltage, which reflects internal losses. All of these efficiencies degrade over time, influenced by temperature, C rate, battery age, depth of discharge, internal resistance, and the specific chemistry. The key idea is that controlling these factors helps maintain long-term battery performance. Lead-acid batteries. Slide 1 of 2, let's take a quick look at how a traditional lead-acid battery works. On the left, we see the battery discharging. Electrons flow from the lead anode to the lead dioxide cathode, and both electrodes gradually turn into lead sulfate as the sulfuric acid in the electrolyte is consumed. On the right is the charging process. When we apply an external power source, the reactions reverse. Lead sulfate is converted back into lead and lead dioxide, and the electrolyte returns to its original sulfuric acid concentration. You'll also notice hydrogen and oxygen gas forming as part of this reversal process. At the bottom, you can see the chemical reactions separated into anode, cathode, and the overall net reaction. You don't need to memorize these now, but feel free to come back to this slide later to review how the charge and discharge equations balance out. Lead-acid batteries. Slide 2 of 2, now, let's wrap up lead-acid batteries with a quick look at their key characteristics and where they're used. Lead-acid is the oldest rechargeable battery technology, and even today it's valued for its reliability, ruggedness, and very cost-effective performance. These batteries can deliver strong bursts of power, which is why they're popular in automotive starting systems. Of course, there are trade-offs. They have low energy density and a shorter cycle life, especially compared to modern chemistries like lithium-ion. And they come in 2 main forms: traditional flooded batteries and sealed maintenance-free versions. In terms of applications, you'll find lead-acid batteries everywhere, from small, low-cost devices to backup power systems to car SLI batteries. The picture here gives you a look at the inside of a commercial lead-acid battery. Nickel-cadmium batteries. Slide 1 of 2, now let's take a look at nickel-cadmium, or NiCd, batteries. These use cadmium as the anode, nickel oxyhydroxide as the cathode, and potassium hydroxide as the electrolyte. During discharge, electrons flow from the cadmium anode to the cathode, forming cadmium hydroxide on one side and nickel hydroxide on the other. When we charge the battery, the reactions reverse, restoring cadmium and nickel oxyhydroxide while the electrolyte stays chemically stable. The diagram here shows both the internal structure of a NiCd cell and the basic reaction paths. You don't need to memorize the chemistry now, just take a moment to look at how the materials interact during charge and discharge. Nickel-cadmium batteries. Slide 2 of 2, here are some real examples of NiCd batteries, the kind you might see in older rechargeable devices or specialized equipment. Compared to lead-acid batteries, NiCd offers higher energy density and a longer lifespan, and they perform reliably across a wide temperature range. However, they also come with drawbacks. the memory effect, which reduces capacity if the battery isn't fully cycled, and, of course, cadmium, which is a toxic heavy metal and a significant environmental concern. Because of their durability and steady discharge behavior, NICD batteries are still used in emergency lighting, power tools, and some aerospace and military applications where reliability is critical. Nickel metal hydride (NiMH) batteries. Slide 1 of 2. Now let's take a look at nickel metal hydride, or NiMH, batteries. These are structurally similar to NICD batteries, but they replace toxic cadmium with a metal hydride material at the anode. The cathode is the same nickel oxyhydroxide, and the electrolyte is potassium hydroxide mixed with water. During discharge, electrons flow from the anode to the cathode. The metal hydride releases hydrogen to form water and electrons, while the cathode converts the nickel hydroxide back to nickel hydroxide. When we charge the battery, the reactions reverse, and both electrodes return to their original chemical states. The diagram here gives you a simple picture of how the anode, cathode, and electrolyte interact. And on the right, you'll see the basic reaction formulas. No need to memorize them now. You can review these equations later in the slides or in your textbook to reinforce the concepts. Nickel metal hydride (NiMH) batteries. Slide 2 of 2. Now let's wrap up NiMH batteries by looking at their key characteristics and their uses. Compared to NICD batteries, NiMH cells offer higher energy density and higher capacity, and they're much more environmentally friendly because they don't use toxic cadmium. They're also far less prone to the memory effect. The trade-offs are a shorter overall lifespan and reduced stability at very high or very low temperatures. In terms of applications, you'll see NiMH batteries in things like digital cameras, hybrid vehicles, and many portable electronics. The image here shows typical commercial NiMH cells in different sizes, similar to what you'd find in everyday consumer devices. Alkaline batteries. Slide 1 of 2. Now let's take a look at alkaline batteries, one of the most common primary battery types. You can see the basic components here: a zinc anode, a manganese dioxide cathode, and a potassium hydroxide electrolyte. During discharge, electrons move from zinc to manganese dioxide through the external circuit, producing electricity that powers the device. The chemical equations shown on the slide outline these reactions, but you don't need to memorize them. Just remember that the anode forms zinc oxide while the cathode converts to a different manganese compound. The diagram on the right helps visualize the movement of electrons and ions inside the cell. When you review the slide or the textbook later, take a moment to walk through how the ions circulate and how the separator keeps the two sides apart. We'll continue exploring their characteristics and applications in the next slide. Alkaline batteries. Slide 2 of 2. Now let's take a quick look at the characteristics and common uses of alkaline batteries. These are primary, meaning they're not rechargeable, and once they're depleted, they're discarded. They offer moderate to low power density and a low self-discharge rate, which is why they can sit in storage for long periods and still work. But because they're single-use, they create environmental concerns. You can see their structure and appearance in the images on the slide. This is the typical alkaline cell most of us know from everyday devices. And that leads to their main applications: remote controls, flashlights, portable radios, and toys. Basically, anything that needs inexpensive, easy-to-replace power. Lithium-ion batteries. Slide 1 of 2. Now let's move into lithium-ion batteries, the core technology behind today's EV and ESS systems. A Li-ion cell is built from three main components: a graphite anode, a lithium metal oxide cathode, such as LiCoO2, and an electrolyte containing a lithium salt such as LiPF6. During discharge, the battery is powering a device. Electrons flow externally from the anode to the cathode, while lithium ions move internally through the electrolyte toward the cathode. The graphite releases its lithium, and the lithium combines with the metal oxide structure in the cathode. During charging, everything reverses. The external power source pushes electrons back to the anode, and lithium ions move from the cathode and intercalate into the graphite layers. The diagrams on this slide illustrate both directions of ion and electron flow, and the chemical equations summarize these reactions. You don't need to memorize the equations, but it's helpful to recognize how the anode and cathode exchange lithium during each cycle. When you review this slide and the textbook later, take a closer look at how these reactions define the cell's behavior. Lithium-ion batteries, slide 2 of 2. Now, let's wrap up with some key characteristics of lithium-ion batteries. These cells stand out because of their high energy density, low self-discharge, and long cycle life, which is why they dominate EVs and portable electronics. They're also lightweight and come in several different formats: cylindrical, prismatic, pouch, and even button cells, as you can see in the image. That versatility allows manufacturers to design battery systems that fit everything from smartphones to large EV packs. One important point is that Li-ion cells require protection systems, like BMS controls, to prevent issues such as overcharge, overtemperature, or excessive voltage. And of course, some cobalt-based chemistries can be more expensive. In terms of applications, Li-ion batteries are everywhere today: consumer electronics, electric vehicles, and grid-level energy storage systems. They deliver the performance and reliability required across all these sectors. Lithium-ion batteries, cathode chemical variants. Lithium-ion batteries come in several cathode chemistries, each with a very different personality. On this slide, we have 6 of the most common types: LCO, LMO, LFP, NMC, NCA, and LTO, and I'll briefly touch on each. LCO offers high energy density, so it's widely used in consumer electronics. LMO and LFP focus more on safety and long lifespan, making them strong choices for automotive and ESS applications. NMC has become one of the most popular EV chemistries because it balances energy density, safety, and durability. NCA also delivers very high energy density, which is why you see it in many electric vehicles. And LTO is the standout for extreme safety and thermal stability, ideal for specialized uses like medical or military equipment. The radar charts in the image compare these chemistries across 6 dimensions: specific energy, specific power, safety, performance, lifespan, and cost. Each one has trade-offs, and understanding these helps engineers choose the right chemistry for the right application. Key characteristics for choosing batteries, slide 1 of 3. When selecting batteries for any application, a few fundamental characteristics really guide the decision. First is the type, whether it's a primary battery you use once or a secondary battery you can recharge. We also look at voltage, which is determined by the active materials used in the electrodes. The discharge curve is another big one. A flatter curve means the battery delivers a steady, predictable voltage instead of dropping off quickly. Then, of course, there's capacity, which tells us how much energy the battery can store, and energy density and power density, which describe how much energy or power the battery delivers for its size or weight. Finally, temperature matters a lot. As the temperature drops, chemical reactions slow down and internal resistance increases. The graph on the right clearly shows this. The green line represents cold conditions, with lower voltage and a much shorter discharge time, while the red line shows the best performance at higher temperatures. So, when choosing a battery, all these characteristics come together to determine how well it will perform in a real-world environment. Key characteristics for choosing batteries, slide 2 of 3. When we talk about a battery's service life, we combine 2 concepts: cycle life, which is how many charge-discharge cycles the battery can handle before it drops to about 80% of its original capacity, and shelf life, which is how long a battery can sit unused and still retain most of its charge. A few key factors have a major impact on service life. Overcharging or overdischarging generates heat and causes chemical degradation. Deep discharges, what we call high depth of discharge, are especially damaging, and you can see that clearly in the graph on the right. The deeper the discharge, the shorter the cycle life. High current loads, extreme temperatures, physical shock, and vibration also accelerate wear. And even under ideal conditions, all batteries naturally age over time. So, when selecting or managing batteries, minimizing stress and controlling operating conditions goes a long way toward extending their useful life. Key characteristics for choosing batteries, slide 3 of 3 now. As we wrap up the key characteristics for selecting the right battery, the last group of considerations focuses on how the battery will actually be used in the real world. First, the charge and discharge cycle matters: how long it takes, how easy it is to access charging, and any safety risks during the process. Then we look at the physical requirements, the size, shape, weight, and terminal positions, to fit the product or system without compromise. Cost is another big factor. It includes not only the initial purchase or manufacturing cost, but also the ongoing cost of charging and maintaining the battery. And finally, application requirements. Each application, whether it's an EV, a drone, or a home storage system, has specific needs for voltage, current, capacity, and power or energy density. The right battery is the one that meets those needs at the lowest practical cost. The image on this slide breaks down what actually makes up the cost of an EV battery cell. You can see that the cathode alone accounts for more than half of the total cost, making it the single largest cost driver. The anode, separator, and electrolyte make up much smaller portions, while manufacturing accounts for about a quarter. This cost structure is a major reason why cathode chemistry and material prices are so influential in the EV market. Here at the end, you'll find the list of references and sources used throughout this chapter. These include technical diagrams, data charts, and images that supported the explanations we covered. I won't go through them individually, but feel free to look through them on your own if you'd like to explore any topic further. And with that, we've completed Chapter 1, Introduction to Batteries. Great job following along, and let's continue building from this foundation in the next chapter. Thank you. We'll meet again in the next lecture. Thank you. We'll meet again in the next lecture.